The broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon, everybody. The time will be 3:35, so let us get going. Let's see, we've got about 16 people in here. We'll see if that will increase, but definitely time to get going. I see a couple of repeat customers from our Tuesday adventure. So as the little background slide there indicates, we are day 2 of the Inspire in Motion training. The reason we named that Inspire in Motion was because we're going to, for the first time in this EDU webinar series, introduce the motion capabilities of Inspire. So the Tuesday version of this class dealt entirely with just kind of getting around in Inspire, bringing in geometry, setting that geometry up for analysis and for optimization, and then reviewing those results, whether we're talking about doing a structural analysis or doing a structural analysis leading into an optimization. So we covered kind of the basics of using Inspire for what it was originally written for. But today we're going to devote entirely to setting up motion analysis in Inspire. So yeah, it wasn't too long ago, maybe a year and a half ago, we introduced the capability for motion analysis in Inspire. And as far as I'm concerned, that was kind of a game changer for the whole Inspire thing. Inspire has always been a phenomenal tool, bringing analysis and optimization kind of to the masses, taking it out of that kind of hidden dark realm of people, the few people who were aware of what FEA was, how to do it, how to set things up, and really exposed the ability to do high-end, very accurate analysis and optimization. Exposed it to people who previously that kind of information was beyond their knowledge base. So another, I won't say mystical art, but another not widely available capability that was limited to those who were educated in motion analysis is, well, motion analysis. We have a software, Motion View, which is our preprocessor, and Motion Solve, which is our actual processor for analyzing dynamic systems. So we're talking about things that are moving. Just for instance, if you think automobiles, you got your suspension system along with the steering wheel. So you can simulate all of that. You can actually simulate the action of putting your hands on the steering wheel and turning it and causing the wheels to go left and right, hitting bumps and the shock absorbers and all that sort of fun stuff. So basically anything that moves, any system that moves, we can simulate using a motion analysis. But it was, I always hesitate to say difficult because I don't want to make our software sound difficult, but it was not the easiest. It took some time, it took some knowledge of how motion worked, and you'd have to learn the software, and it would take some time to do it. Now, once, of course, you became proficient at it, Motion View is a very easy software to use, but there's a lot of time involved in getting proficient, as with any high-end analysis preprocessor. So we said, hey, why can't we take this complex motion analysis stuff and move it into Inspire, where we can set things up very easily? And so we did, and it really, really changed things. It allowed us the capability of not only testing dynamic systems and seeing how they behaved, but allowed us then to very easily do things like tune springs and figure out what a good spring rate is, or use that motion analysis not only to make sure that the kinematics of your system works, but then use that information to automatically calculate loads and forces and feed analyses and optimizations through that. So it's really, really tremendously, and I mean, sound like somebody uses a lot of adjectives, but it tremendously increased the capabilities of Inspire. And so that's what we're going to address today. We're going to talk about how easy it is to bring in geometry and set up studies. We'll start with simple and move to a little bit more complex and wrap things up kind of taking just the geometry and going to a relatively complex motion analysis where we're going to have contacts and we're going to have motors and we're going to have all sorts of fun stuff there. So a couple of things, of course, before we start. So let me get out of that screen there, and we'll bring up this slide right here. So let me maximize that. So again, if you're new to if you came on Tuesday, I'm still the same person I was on Tuesday. But if you're new to this session, my name is Eric Larson. I am the Technical Account Manager for Education at Altair. I work with universities, with competitive design teams, with students, with faculty, with whomever is involved in education, and showing them how to utilize our software to improve the educational process, and then also with competitive teams to make your vehicles or whatever you're looking to design for your competition better, lighter, stronger, and just generally better. A couple of notes here. Everyone is muted. When you entered, the system automatically muted you. Please don't take offense to that. It's just a matter of making sure that there are no background noises to take away from the seminar here. If you want to ask a question, and hopefully you do. I always like it when there's a bit of interactivity between myself and the audience members here. But if you want to ask a question, as it says there, please feel free to use the question window, and I will answer them as they come in or at an appropriate time through the webinar to answer questions. If you don't want to type and you kind of want to have a back and forth, and you want to talk, I'm always open to that. I believe on your audio or on your attendee window, there's a little raise your hand button. If you click that, it's going to raise your hand. It's going to let me know that you want to talk. I can unmute you, and we can have a conversation that way. So whichever way works for you. I know that the vast majority of people just prefer to do it in the questions section, which is totally fine. But if you want to talk, please feel free to do that. And the last but not least, before we get started, and we'll address this again at the end of the webinar, if you are involved in a competitive design team, so I'm talking things like the SAE program where you have your Baja cars and your Formula cars and your clean snowmobile, and I think SAE also does some flying competitions. I know there's that design print fly for the 3D printing. There's rocketry competitions. Go to ASME, they've got their human powered vehicle competitions and their robot competitions. Basically, if you are involved in any team, university team, competitive team, we'd love to sponsor you. And we do that by providing you with as many licenses of the software as you need. And these are corporate level licenses, so there are no restrictions to them. You can use any and all of our software, and we'll get them as many as you need. It's a very simple process. You'll see the link there. Just go to, obviously you can't click on that link, so it's just a background there, but altairuniversity.com, and you just log into that, or you can type in the sponsorship app after that. If you are not involved in a team and just want to get your hands on the student version of Inspire or a number of our other products, again, just go to altairuniversity.com and you'll see a big thing there that says, hey, get the student version. That too is a very simple process. Just fill out a quick form, and we'll get that to you really quick. Some of our softwares do have a little bit of a limitation on them. HyperMesh, our FE preprocessor, for instance, is limited to 100,000 nodes, but that in and of itself is a pretty generous limitation. But the Inspire software that we're going to be talking about today has absolutely no limitation. It is the full version of Inspire, albeit it is a slightly older version because it does take a little bit of time for them to adapt it to use the student licenses. But if you don't mind being a release or point release back a bit, that's another opportunity for you there as well. But you definitely, if you are involved in a team, just go the sponsorship route because you get the full-blown app, and that's where we're going to go from there. So that'll be the end of that. And the next thing, let me come to back. Oops, sorry, I need to escape to get out of that window. There we go. I'm going to come back to the chat window. I know that if you came in after the last time I posted this link, you won't see it in the chat window. So I just put the link to download the class material for this class. It is our full motion class. And let me state what we're going to go over in these 2 hours that we have is a brief introduction into the motion capabilities. We actually have a full day class that we teach. Sometimes online, you can find those classes online, but also in person. And that is the material for that full class. So we're not going to come anywhere near to covering all the material that's in there. I'm going to use 1 or 2 models. But if you want to go through the class, you've got all the material there. And finally, that class material is for the version 2019 version of Inspire. That's not to say that it will necessarily not work in a previous version, but there is the possibility. And unlike the last class where I was able to dig up the older version of the material and put that on a link as well, unfortunately, there is no older version of this material. This material was introduced for 2019, and we do not have an older version. So I apologize if you can't get it to run. But if you get yourself a sponsorship for your team, you can absolutely get the latest and absolute greatest version of the software. That being said, before we get going, just put it out there. Anybody have any quick questions about the class, about anything before we get started? We'll give a second here. Oh, somebody does. So let's see what we have here. What is the typical cost for the whole day class? Do university teams get a discount? The typical cost for the whole day class, for the most part, is free for students. Our online version, no matter whether you're a student or a corporate customer, is absolutely free. For university teams, we can't give you a discount because we're not charging you anything anyway. So you'll pay the full price of $0.00. But what I would suggest is if you want to get the full training class, take a look at our online classes. If you go to altairhyperworks.com, and I can bring that up and show you where that is. We'll do that towards the end of the class. Go to altairhyperworks.com. You can see the online schedule. But if you are with a competitive, so you said university team, so I assume you are. If you get in touch with me, we can talk about setting up either a webinar, or I could possibly even come out there and visit you and do a training as well. So if you want to get in touch with me, please don't spam me, but I'll put my my email here. Oops. There you go. So if you want to just get in touch with me directly, just drop me an email and we can talk about setting up a visit or a webinar or whatever works for everybody. Next question here. May I know until when is the free version valid? So when you get the student version, if you download the student version, and it is important that you download the student version from altairuniversity.com. I know there's a couple of other ways you can get a student version, but please get the student version from altairuniversity.com. Whether you go the student version or the sponsorship, that will be valid for an entire year, and you can renew that every year as long as you are still a student and have a student ID, or not a student ID, but a student email address. I know there's some software, some companies out there that require you to send in like a copy of your schedule or a copy of your student ID. We trust you. We just need to know that when we send you that license, it's going to an email address that is a .edu email address, and that's how we verify that you're a student. So that you'll get it for a year from the date that it's issued, and you can continually renew that. And that is just about it for the initial questions. Of course, at any point in time, please do not hesitate to ask any questions, and I am happy to, oh, you're very welcome. I am happy to address any of the questions that you had at any point in time. One more thing, as I mentioned on Tuesday, let's just take a quick look inside the folder that you've got here. So if you download that zip file and you unpack it, this is what you're going to get. A directory called Inspire Motion Intro. And in there you will find 3 subdirectories. Exercise is going to contain all of the models that are necessary for the exercise, or for the exercises in the manual. Exercise solved, as I kind of referenced it on Tuesday, is kind of like the answers at the back of the book. It is the result, or it's the model in the state it would be had you run through the exercise. And then if you go to the PDF slide, we don't have a total one where they're all assembled, so these are all just the individual chapters. If you go to any of the chapters, so we grab chapter 3 here, for instance, it's going to be an outline of all the things that were in that chapter, so kind of the notes for the chapter, and then at the end of every chapter, you will find an exercise, and you can run through that exercise to kind of self-teach yourself. But I do encourage you, if you're on a team, please get in touch with me, drop me an email, and I'd love to set up either a web version of the class, or possibly, hopefully, even get out there to visit you and do kind of a training consultation type thing. Oops, it looks like we got another question here. If we have the class during a webinar we signed up for, do we still get the recording for that session? Now, so these things will be these webinars that we're doing, this EDU webinar series, is being recorded, and we will send you the recording. We typically don't make that totally public because we really encourage people to attend live as opposed to just registering to get the recorded version. But that, whatever, we know that people's schedules get tight. So yes, we are recording these webinar series here, and they will be made available at the end of the series. But our normal online classes, those are not recorded. Those do require that you attend live. So yes, if you were needed to leave now, please don't. But if you needed to leave now, this class is being recorded, and each one of the webinars is. But our normal online classes are not being recorded. So just make sure you sign up for it, and then you'll get an email link at the end of the whole thing saying, "Hey, here are all the videos." And that's pretty much it. Also, let me just expand this out. Maya, who just asked that last question, as I was going through the attendee, or the people who registered, your name stuck out just because I noticed that you had an MTU email address. Just to let you know, I do go to Michigan Tech a couple of times a year, and I'll be up there sometime in the October-November timeframe. So if you have any questions or want to go over stuff, I'd be happy to meet up with you at some point in time if you're on a team, or just if you just have some questions. So drop me an email, and we can I can help you out there as well. Do you have HyperMesh online recording? No, we do not have any of our standard classes in a recorded format. The webinar series, I think they're doing HyperMesh, and so that would be recorded, the two-hour sessions that we did. So those would be recorded, but the full, well, honestly, for our online class, it's 5 2-hour sessions. We do not have those recorded. Someday we may look into recording if we can find a way to kind of control the recordings, but right now we don't. Okay, so yeah, that's all of the stuff. Let us dive straight into Inspire Motion. So what I've got here, I just loaded up the file that was from this, if you go into Inspire Motion Intro, exercise, the inverted pendulum, I just loaded up this stmod file right here. And I hid this guide bar for right now. So, because we'll get back to the guide bar. So what I have here is a pendulum. And I want to analyze this. I want to see this pendulum go. I want to watch it swing back and forth. That would be fun. So if I were to do this in Motion View, it would take a little bit of setup, but in Inspire, it's pretty easy. All I need to do is bring in the geometry. So this geometry here could have been created in any of the popular CAD packages out there. I know SolidWorks is the big one with the universities, but this could have been created in any CAD package. Essentially, just design the system that you want to analyze. Create the geometry for it, which if you're designing something, you probably already have that generated. And then all you need to do is come in here to File, Open, and open it. And you'll see we support all of these different CAD files in their native format, or you can always go with the intermediates, the Parasolid, either binary or ASCII, step, or where is it hiding at? There it is, IGES. So those are the three popular intermediate formats. Parasolid and step, definitely the preferred method. IGES would be the last resort method. So you just open up that file, and the geometry is going to come in. It will stay sorted into whatever layers or parts or however you have it organized in your CAD system, and the names of those usually will come in as well. And if you attended on Tuesday or are familiar with Inspire, we talked about how to go through and set up a structural analysis, so I could analyze that. But today we're going to go to Motion, which means we're going to come to this little Motion tab right here. The first three icons here are the same as they were in Inspire, but everything else is going to be a little bit different. It's all going to be pertaining to motion. So motion analysis is going to take into account the behavior of this, the movement of it, and it means that we have to now define things or define the interactions of the different parts that we have. And we need to make sure we define those interactions correctly so that we can get the proper motion. So if we take a look at this right here, if I want to analyze this pendulum, and I were to just analyze this right now, these are just three, 1, 2, oops, well, there's a pin in there, 2, 3 individual solid geometries. So if I wanted to analyze the motion on this, and I did that, let me set it for just 1 second, and so it goes a little faster. I'll animate it when it's finished. So I'll click the analysis. That should happen pretty quickly. So the motion happened, that's all set up. So let me see what this thing looks like when it moves, and whoa, it just falls away. So that's kind of our first clue as to where we need to go here, and that is anytime you set up motion, or just about, I know there are very few exceptions to that, but we'll say essentially in every motion analysis, you need to establish something that's grounded, something that's not going to move. So in this case, since we're analyzing the pendulum, it's this little guy up here. That's going to be our grounded part. And you'll notice the very first icon in this kind of process-driven approach is the ground. So if I want to ground this, all I need to do is come up and activate ground. You see my pointer now has this little modifier showing a little ground symbol on it. And when I click on that geometry, if I look over here in the model browser, if you don't have the model browser up, you can either go to View and click Model Browser and Property Editor, or just click F2 and F3. I think these are absolutely invaluable things to have up. I highly encourage you to have them up. You lose a little bit of graphic window, but the information here is priceless. But you'll notice slider now has the little ground symbol on it. And if I were to analyze the motion again, I think you can pretty much figure out what's going to happen here. If I analyze it, whoop, there goes my pendulum. And this, though, stays perfectly still. And the reason it stays perfectly still, of course, is because it's been grounded. But the act of grounding it now has provided me something that my motion can move relative to, something that's going to hold in place that this can be moved against. So now if we move to the next icon here, we end up at this rigid groups icon. So rigid groups, we're not going to use that all the time. But let me explain what rigid groups does. Say, for instance, when I came in here and I defined this geometry, and I defined my pendulum as a rod and a weight on the bottom. And say I define those as separate solids. They would be free to move separately. So my pendulum could come swinging down, my rod could stop, but the ball, the weight, is just going to continue swinging. And in fact, it wouldn't even swing if I were to do this and set it up properly. My rod should swing like this, and the ball, the weight, would just drop down. So there's some way that I need to connect these together, and there are ways that I can. I can define joints between them, contacts. But if I truly want something to act just as a single unit, the most mathematically efficient way of doing that is to define them as a rigid group. And essentially, it's just like taking and gluing them together. They still can move, but they all move together. So it would be as if I glued or welded the rod to the end here. So this isn't something we're always going to do. In fact, we're not going to use it here because you'll see my pendulum is just one solid entity, so I don't need to bother with that. But if you truly need something to act in unison and it's not one single solid, you'll need to define rigid groups. The next thing, though, I absolutely need to define. So if we, again, take a look at my behavior here, you see my pendulum is just sliding out of there. Well, this pin, it's in there, but there is no contact between the pin and this block here. There's nothing saying that it can't move or that it has to stay inside there. So I could technically define that as a contact, but I don't want to. And the reason I don't want to is because I just need this to act as a simple joint. Just allow it to revolve in there. Contact would work, but it's more mathematically intensive than a simple joint. So if you have something that you just want to act as a simple joint, you don't want to you don't need to define a contact between the two. You just want it to act as a joint. Joint is the way to go. So if I click the joints here, you see it automatically detects that pin going through the hole. And if I click that, it defines it as a cylindrical joint. Now, if I come here, and you see I lost the little check up here because I've changed something. Now, if I come and I analyze the motion, the pin stays there because the joint is allowing it, or is keeping it there, but my pendulum now leaves. So come back to joints, and the reason was this is actually two joints in here, and I need to click that, and it's defined cylindrical as well. You'll see we have a number of different joints: hinge, cylindrical, translational, ball and socket. And you would just define it however you want that. And now, if I run this, you'll see that my pendulum does that, which of course makes absolutely no sense. And the reason for that is because the orientation of gravity. So you can see I'm kind of stepping through this and getting closer and closer and closer. The last thing I want to do here is come to my gravity. You will see a big blue arrow indicating the direction of gravity. Gravity is pointing in the negative z direction. I actually want it to point in the positive z direction. So I just click the plus minus, or I could point it in the x or the z or the y, or I could even come in here and rotate it to a special angle or degree, but I just want it in the Z and I want it in the negative. And my acceleration due to gravity, because I'm using millimeters, newtons, and seconds, is going to be 9,806.65 millimeters per second squared. And I right click to get out of there. And now I analyze my motion and I play it. And there's my pendulum. So in 1 second, it makes it to there and then makes it part of the way back. Now that I have that, I can come back up to my motion, click this little button here, and I could have it run for however long I want. Output rate is how often it's going to take readings during that second or 2 seconds or whatever. So I'm going to get 30 different readings. And when I animate this, you can kind of see those, and it's why it's a little bit choppy. If I come here instead of 30, say 100, and I run it, it will take a little bit longer to run. It won't take too long because it's just simple, but you notice how it's taking a little bit longer to run. But now you'll see I get a smoother behavior out of this because it's split it now into 100 different time slices. So I get a little bit smoother of a behavior. So we do kind of a balancing act here between how long we want it to run and how much information we want out of that. So I've actually now have my first analysis run. It's as easy as that. Now you notice though that my pointer has that little, looks like a little graph symbol on it. Let me pause this and let me click that right there, and you'll see as soon as I do that, it puts a graph up here. And if I double click it, I get a better graph. So this is showing me the displacement. So let's animate this. And I can see the displacement of that pendulum in the X, the Y, the Z, and then the overall magnitude. And if I right click on this, I can actually see all the different things that I can do. So let's say angular displacement. So now I'm getting the angular displacement or the velocity. Let me close that. I could come in here, click on that joint. I can see the velocity of the joint. I can get all sorts of interesting information off of this. Well, let's make this a little more interesting now. Well, before we do that, are there any questions about what we've done? And I promise you, we will get to couplers and motors and actuators, springs. Okay. Well, let's do this now. Let's make this a little more interesting, a little more fun. I'm going to come here, and I'm going to come to geometry, and I'm going to do a sketch, and I'm going to say I want to sketch on this face right here. We're going to create a new part, and I'm going to come and look at it kind of end on here, and I am going to draw a big wall here. And we'll right click on that. That should be enough, and right click on it again to enter the push pull, and I'll just drag this out just a little bit. Doesn't need to be real thick. Oh, come on. Grab it. There we go. Yeah, it doesn't matter. And now right click again. Now, if I were to run this, can you guess what's going to happen? Oh, here, what do we got? A question. When I show the velocity of the position, which the rotational one, can I change that? Yeah, let me take a look. When unfortunately, because I've lost my motion run because I did something to this. So once I get back to that, we'll take a look at that. So as I've got this right here, can you guess what's going to happen? Let's see if your guesses are correct. So let me run the analysis real quick. And I'll play this. So if you guess the pendulum's going to act exactly the way it was and my big old slab there is going to fall, you got it right. So what I need to do now is I need to come back to here and I'm going to ground this. So I'm going to add that to the ground. Now that's going to stay put. It's not going to move. And if I analyze the motion, can you guess what's going to happen now? Well, if you guessed, first of all, that my wall is too short, but second of all, that the pendulum just goes ahead and passes through it, well, you got that one right as well. The wall's there, but there's nothing telling it that the pendulum can't pass through it. So I need to, well, first of all, I'm going to come here and double click on the bottom of this. I'm going to drag that out a little further so I can guarantee that the weight on my pendulum hits it. And then what I'm going to need to do is I'm going to need to tell it that I do not want this pendulum ball to pass through this wall. And I do that through the use of contacts. So I come here to my contact. It's going to ask for two parts. I'm going to pick my moving part there, my stationary part right here. I'm going to click Create Contact, and it's going to put this little contact symbol in there. It's going to be an impact collision type. And now watch what happens. When I run the analysis and I click play, bam, it hits it and stops. And if I were to instead now come here and let's change my optimization parameters. Let's go down to 50 so it doesn't take long. And let's run this for 5 seconds instead of 1. So it'll take a little bit longer because I've got 5 seconds. And you'll see every once in a while it's going to pause a little bit. More than likely, each one of those times that it's pausing, it's having to calculate a new contact, because now when I run this, I can see the behavior of that slowing down. Now, you had said, so if I come here to my pin and do the plot, I've got my velocity. So I can do velocity. I'm assuming that's rotational velocity. I can get angular velocity off of that, but that would be the only thing that I've got. Now you can work with these contacts. So if I come here to the contact, I can actually see the normal force of the contact. So by clicking on that contact, I can see that it's receiving a bit over 700 newtons. If I come here and put my cursor on there, I can find it was 713.81 newtons as a result of that ball coming down and hitting it. And if I'm now interested in this, I could right click on this and I could export this as either a CSV or just an image. I can also come here, and if I click this little run option and click Force Explorer, what it's going to do is, maybe I need to pause. Let me pause this. So each time that it hits, and instantaneously when it hits, it pops up a little vector there showing me what the force on that contact is and the direction it's going. And one would hope then that if I come to here, there it is, 70.5. So that's that spike that I was getting. So I can visualize the contacts as well, or the force of the contact. And you see it, the vector corresponds to the magnitude of the force. So we can get some pretty interesting information out of this. So let me exit the thing. We're going to turn off my Force Explorer. And if we take a look at the contact, we can manipulate the stiffness, the damping, and the penetration depth of the contact so we can fine tune that contact. So that's kind of the basics of it. We much more to go, but that's the basics of setting up a motion. You just work your way across here and apply the things that are needed. And on almost every case, we're going to start with the ground. So this next set here, I'm going to come here and I'm going to delete that. I want that gone. You see it deleted it off of there. It also got rid of the contact because now the contact doesn't make sense since half of the geometry that represented the contact is now gone. And I'm going to come here to guide bar and I'm going to turn that guide bar on. Now that guide bar has been there all along. You see in the background I just established it as ground. So that guide bar is effectively useless because of the fact that my slider was ground. But let's come here to my slider and I'm going to turn off ground. Now, and I'm not going to do it, I don't need to waste the time, but now hopefully at this point in time, you would take a look at this and you'd think, okay, this is just going to fall right down through there. So I could define a contact, but again, I want to do this as mathematically efficient as possible. And in this case, the best way to do it is actually to define a joint. So if I come here, you'll see now it recognizes this rectangle. And if I click that, it establishes it as a translational joint. So now we should see some kind of interesting behavior here. So let me do this and let me do the run. We'll take it down to 2 seconds just to slow the run down or keep the run quick enough. So our friend Isaac Newton here had something to say about this. So we're getting an action reaction here. So this slider is now moving across because the pendulum is doing that. Now this probably would go on to infinity because we've got nothing preventing this from stopping. But I could come here to my translational contact, or darn it, stop it. So let me get out of here. Come to my translational joint. And do we have the ability to do? No, it's just through contacts that we have friction. Is there? No, not pretension. Thought we had friction. I guess we don't have friction in the joints yet. But let's do this instead. Let us come here, and if I come here, and I'm going to come to spring, and I'm going to select the center of that line as one end of the spring, and the center of that is another. I'm going to put a spring there. And now come out of this, and now let's analyze the motion. Let's see what happens now. Okay, so that's a relatively stiff spring. Let's lighten that up a little bit. So I'm going to come to my coil spring here, 1 Newton per millimeter, and let's make it 0.01 Newton per millimeter, and analyze the motion. So we get a little bit more movement out of there. There we go. So now the spring has essentially damped out the entire thing, because that's going to start absorbing the energy of the pendulum moving back and forth. So let's take a look at that spring that we created. It actually did quite a bit in the creation of that spring. So I've got a spring, I've got a damper in there, I've got a stiffness, but you'll notice that it automatically calculated the free length. So it measured from the 2 points that I put there, and it said that's the free length. So in its complete state, if I had my ball, my pendulum ball hanging straight down, and I ran this, nothing would happen because the spring would be in its complete free state. So you notice there's no preload on there. Well, if I come here, let me put a Newton preload on there. I want you to watch this free length right there. When I do that, you see it automatically updated the free length. So it calculated what the length of that spring should be to put a 1 Newton preload on there with a stiffness of 0.01 newtons per millimeter, and surprise, surprise, it was 100 millimeters. Pretty easy calculation there. But now if I run it, it is thinking that the spring is already compressed, that its free length is somewhere down here. And now if I analyze it, you see it shoves it out. So springs are pretty cool in here as well. And if I come back to the spring, let me make the preload 0 again. Well, we'll change this to 284. You see it automatically calculated. It's just under 1 Newton because I just ignored the, I could have made it 284.353. But we can go that route to preload. So you could, if you say you wanted to model an unbalanced spring mass system, you could do it, and you could say that the free length of the spring is different than what the actual measurement is, and it would automatically start oscillating that mass back and forth. Make sense? Hopefully. Any questions about springs? Okay, so now let me try something else. Let's delete that spring. Let's make it go away altogether. And instead of a spring, I'm going to put an actuator on here. So when we need to simulate movement other than that which is driven by gravity, we do so through the use of either an actuator if that movement is linear, or a motor if that movement is rotational. We'll get to motors in the next model that I bring up. But let me do the actuator right now. So my actuator, not connected parts, I'm going to say features. So my actuator, I want to run from here. Oops, darn it. And try that again. Actuator, I want to run from here to there. And let me flip it around. And it's saying 61 millimeters. And it's going to push it in this direction. Let's, so we don't push it off the end, let's just make that 20 millimeters. Actually, you know what? I'm going to come here to my measure. Let's just measure the distance from here to the end of here. Oh, 183, so 61 is fine. So I'll come to my actuator. We'll do a displacement of 61. Now, how do I want that displacement to happen? Step dwell step is going to go out and then come back. If I just do a step, and I'm going to say I want this to occur over 1 second, and for whatever reason it's locked, I don't want that. And then I need, if I do this right now, not much is going to happen, because as it pushes this out, it's going to want to reorient itself, but my pivot is fixed, which means it has to stay in that orientation. If I make it a revolute, that will just allow that the end of this to revolve. And now if I analyze the motion, review, what did I do here? So it did not like that. Let's see what it came up with. So where did things go wrong? I suspect that the actuator was trying to put a little bit of force on that, trying to push it down through there. But so if I instead kind of made it a little more, as opposed to angular, made it a little more linear, running straight from here, it should work better. But I suspect that that angle is causing, oh, I know, oh, you know what? No, that was just me being stupid. If I come here to my actuator, I didn't want revolute, I wanted spherical. Revolute is going to just allow it to rotate that way. I need it to rotate spherically. Let me run the motion again. This should work now. Yeah, so now as it's moving, it's pulling that back, or it's pushing it out. If I come here and change the actuator to a step, and we can see the force required on the actuator. If I come and change this to, as opposed to a step, we'll do a step, dwell, step. It's going to go out, start at 0, go out for a half a second, dwell for a second, and come back in a half a second. And just to make it a little more fun, let's make it 100 millimeters. And now run it. And now we can see go out, pause, and come back. So if we continued this going back and forth, maybe make it oscillating, we could start putting some energy into the pendulum and cause it to swing on its own. So this is how we can create movement within within a system. Like I said, we'll get to rotational movement with the next model, but that's just linear movement. Questions? Okay. Let's look at something a little more interesting than just a swing and pendulum here. Open. So these are just some of my demo models. You actually don't have these, but just to show you some of the cool things that we can do. Yeah, landing gear, that's a... That should be a fun one. It's a bit of a complex model, so it's just going to take a minute here to load up, so just bear with me. There we go, it's almost there. Excellent. Okay, so we have a landing gear. This is an actual model of a landing gear from the A380 jet. And this was just brought in as geometry. One thing that I neglected to mention, and I apologize for that. Actually, before we do that, let me bring that pendulum model up just one more time. It's because I forgot to show you this. We had that pin modeled in there. That came in as geometry. That is absolutely not necessary. So the geometry on this pin, if I delete that, so I'm going to click my delete button. So if I just have a hole here and I come to my joints, it's not going to show anything. And the only reason it's doing that is because you notice there's a pretty sizable gap between my pendulum rod and the edge of that. If I come here and I come to options, I can create a search distance. We'll say 5 millimeters, or not 5 meters. And now find, I gotta go bigger than that, options. Let's try 20 millimeters. And find, it's still not doing it. Okay, then I'm just going to do it manually. I could play with that, and what it will end up doing is finding these holes, but since it didn't, I'll just add them manually. If I click on these holes, you see they turn red. Now if I click again, it identifies those holes and it will put its own pin in there. So I don't have to have the geometry. Now if I come here and I set that as ground and I come to my motion parameters, 1 second, close, and my gravity, send it the other way around and run the analysis. Oh, and guess what I forgot to do? Ground that. There we go. And now run the analysis, and now we get the pendulum behavior. So we do not have to have the geometry for joints, and that's what we've got in here. If I zoom into here, you see that it has created these pins for us. So it looks for geometry that represents a joint, or geometry that would be conducive to having a joint put in it. But let's take a look at the behavior of this. You'll notice this is pretty complex. I've got, oh, stop it, get out of there. I've got a ton of joints, and I've got what, 1, 2, 3, 4, 5, 6, 7 actuators on this, and each one of these actuators is staged. So this one starts at time 0. This one waits until the first one's done, so time 6. So I can create some relatively complex behavior. And now if we take a look at the motion on this, you'll see those actuators will begin to engage. It's going to start drawing the gear up into the bay here, and then other actuators will begin to engage. So as it comes up at an angle, it's going to begin to horizontally orient that landing gear so it can fit into more compact of a landing bay, or a gear bay here. So we're going to get that kind of horizontal action there, and that's another set of actuators that's actuating after the first one. Once everything gets situated in here after 6 seconds of analysis time, then the actuators on the door flaps here are going to engage, and the door flaps will begin to close. So we can set up a pretty complex model. Now, if I wanted to run an analysis off of this, well, let's take a look at this joint here. If I click at the joint, you see it's calculating the force on that joint at every instance. So whatever my sampling rate is, it's calculating a force there. So not only can I get joint forces and make sure that I'm not exceeding some sort of level, but I could use that joint force and I could drive an analysis from that. So if I come here to analyze, and I tell it I want to run an analysis on this part right here, you see what it's going to do is, if I click this, use all 360 time samples. Well, 360 time samples, I ran this for 9 seconds at an output rate of 400 hertz, so that's 360 pieces of information. That joint, the joints that are connected to this have 360 pieces of information. It will string together 360 360 static analyses, and you can end up with something like this. This would take a while, so I'm not going to run that, but I do have one that I did. It's on another aviation part here. Where is it? It's called flap and spoiler. There it is. So this is one that I did. I just went to GrabCAD, grabbed myself some geometry off there of a wing section, and it had modeled in the geometry for the flap and for the spoiler. If we come down here, I've got 2 actuators in there, so let me hide this. So I've got 2 actuators in here that are going to activate the spoiler. And then I put motors on here, which are going to define the flaps. And if I, oops, darn it, by doing that, I lost my my motion analysis. So let me reload that. Anytime you make any changes to the model, it resets the motion analysis. So I just need to reload it up. But if you take and you run a motion analysis and then save your model instantly after that, the motion analysis is there. So now I come here, and what I did was I ran it, and then I said I wanted the stress calculated on this part right here, and you'll see through the entire motion analysis, I'm now getting the von Mises stress on that part. And I have no clue what the forces on this is. So I used the motion analysis to drive a structural analysis. And I could do the same thing with optimization. So if you remember from Tuesday's class, optimization, what we had to do was just define the parameters for the analysis. Well, that's already taken care of with the motion. And then all I needed to do was define what is my design space and what's my non-design space. So I could cut out a design space here, run an optimization, and it would use the motion analysis to drive an optimization. I got a question here. Is there only gravity applied, or can I define air pressure on the wing as well? Yeah, so unfortunately at this point in time, it's going to be gravity and then forces that are going to come about as a result of the motion. So when I am rotating this, it's causing forces in the pin. I cannot at this point in time utilize actual structural loads, so I can't simulate air pressure on that. So there are going to be some limitations to that. I don't even know if you could do that with motion view, because that's just going to be strictly based on the motion as well. Yeah, at this point in time, they may be in the future, but right now it's just it's loads based on gravity and the motion behavior of the model. Great question though. Okay, so this actually now also introduces a motor. So let me come back here to my motor. Let me turn that back on. And let's exit out of here so we can take a look at the behavior of a motor as well. So a motor, I just applied on that rotating part, and a motor, what we can do is we can specify what type of motor it is. So what is the driving force behind the motor? And whatever one of those you indicate, it will do that. So if I say angle, and in this case, my angle motor is designed to rotate to 45 degrees starting at time 2. So my actuators are going to engage from time 0 to time 2. As soon as that spoiler goes up, then my flap motor will begin to turn, and it's going to turn 45 degrees over the course of 2 seconds, from 2 to 4 seconds. No matter what the torque required, it will turn 45 degrees. So whatever type of motor you set, it will achieve that. Whatever else is required, unless it physically can't. So if I had oriented these little brackets here in a way that it positively locked, it would stop there, and I believe the analysis would say, oh, can't go any further. But if it took 1,000,000 Newton millimeters of torque to turn this, it would do that to get 45 degrees. Or I could come here and define this as a torque. So I could define exactly what the torque of my motor is, and then I could use this to make sure that my motor has appropriate torque to accommodate whatever I'm looking to do. There was underrun a triangle for a force explorer. Yeah, force explorer is right there. Yeah. Is that what you were asking? Hopefully that was what you were asking, just to find that. So that what the force explorer is just telling that all that's doing is it's reporting to you contact forces. So we can fine tune it. Now the motor can be any of those, and what I can do is if I double click on this, I can also not only drive it by a simple controller function. So this is just step. I can also define this through the definition of a table. So it's going to show me what the curve of my motor controller is right now. So 45 degrees, there's my 45 degrees. It's going to start at time 2 and have a smooth ramp up to there. I can actually take these and I can move them, but only once I convert this to a table. So it automatically calculated that curve. If I click convert to a table, what it's going to do is it's now going to say, okay, at start time 2 seconds, this is my curve, and this is my second, and these are my degrees. So I could either come and alter this and make it really bad, or I could put in the actual values here. So I can define this, or I could even open up, if I had them, I could open up in comma separated value the x or the xy. So in this case, second degree behavior of that motor. So I could control it in that way as well. And I have the same thing on an actuator, but in an actuator's case, it's going. Oops, here, let me come to the actuator. In an actuator's case, it's going to be, instead of that. Grab that actuator. Come on. Why won't it grab the actuator? Let's try that again. Nope. Hide. Oh, you know what? Maybe I can just come to here and say no. Where's my, to go to table, and where's, why won't it give me my actuator table here? Let's try this again. There we go. Okay, so now I can come to my actuator table there. I just had to double click on that blue arrow. So now in this case, the table is going to be just X and Y. So seconds versus, or it was X and Y last time, but now it's, as opposed to seconds in degrees, it's going to be seconds in millimeters. And I can see my displacement there. Okay, one more thing I want to show you, and then we'll kind of work on a little project here. I'm going to open up this other model that I created. This is a really nifty new function that was added to Inspire Motion, and it is the coupling function. So hopefully we all know like what a rack and pinion steering system is. A rack and pinion, of course, you're going to turn your steering wheel, but it's going to cause, you're going to take rotational motion, you're going to convert it into linear motion. Now I could simulate that on here. I could create a rod that represents my steering column, and I could connect it to a gear, and then create a gear on my axle, or the my what do you call it, what moves the control arms that causes the steering. So I could physically model a rack and pinion system and then define contacts between the gears. You can see gear contact in the next example that we do. But that's going to take quite a bit to analyze if I'm just if I'm not caring about the behavior of the system, I just want to be able to translate that rotational motion into linear motion. I can do so with a coupler. What a coupler does is it allows me to couple two joints. So if we come and look here, I have a joint between this rod and this block, and it's a cylindrical joint. Don't know which one it is. If I come here, thought there was a way that I can, I don't want to suppress. I want to show it. Oh, you know what? If I come here, I bet you I can do this. There we go. So that joint right there, between this rod and this block, I've got a cylindrical joint. And then I have a translational joint between a little plug that square plug in here and the outer block right there. So those, for convenience sake, I just copied that to here. So you can see that there's this kind of rectangular slot going down through there. I filled that in with a rectangular plug, and I have a translation between there. My coupler is a couple between my rotation and my translation, and I am telling it 360 degrees rotational equals 600 millimeters translational. And what do you have there? You've got a couple between a rotation and a translation. And now if I take a look at the behavior of this, and you can see the couple there. Oh, we just lost power in the building. Hopefully our Wi-Fi is still up. If somebody could just respond in the chat, let me know that I'm still live here. Hopefully. Fingers crossed. Oh, somebody sent. Okay, good. Phew. Okay, yeah, I'm working off my laptop, which is going to have enough power to last me for the next 45 minutes. And as long as the Wi-Fi routers stay up here at the building, I'm still good to go. Working in the dark, but hey, I spend half of my life in the dark, so that's okay. We'll keep going. So, excellent. So now I've showed you, sorry, I just lost my train of thought there. So I showed you the couple. I coupled 360 degrees of motion on my rotation to 600 millimeters of travel on my translation. And look what I have there. I've got rack and pinion steering. Motion, actually any analysis, it's all about simplification. Make things as simple as you can. You don't want to overcomplicate things. I could get this behavior through contacts, but that is going to be very, very computationally intensive. Okay, let me just make sure there's no actual questions here. I'm live. I'm still alive. Okay, good, good, good. Okay, so that's and now that coupler, if you've got prior to version 2019, you will not see that coupler there. That is a brand new feature that we added. Get your hands on 2019 if you want to play with that. Okay, I want to get going on the last demo here, just to make sure that if things go bad here and we lose more power, you're going to get the information. So the last thing I'm going to do is I'm actually going to pull up a model that's in the exercise folder here. Apologize, I just hit my microphone. And it is going to be desktop motion intro exercise, and we're going to come to pulley extension. So we have this nifty little pulley here, pulley extension, and the behavior we want is We drive this gear. This gear will drive this gear. All of this sitting on this little purple thing right here. These little pulley things here are fitted in slots, and they have these bolt little guy looking things here that are fitted in these slots, so you can kind of picture when I rotate this gear, it's going to cause these slots to change their orientation, which is either going to push in or pull out these little pulley arms here. So let's work this together and see what we can get. So I come to motion, and you remember, first thing I want to do is I want to ground. And what's going to ground here is this big purple thing. So now if I were to run the motion, I'd run it, and this purple thing would stay there, and everything else would fall in whatever direction gravity is going. Next thing is rigid groups. I don't have any rigid groups on here. Like I said, we don't always define them. So I'm going to move on to joints. Now joints. Joints I need to define. I'm going to have to define them manually because it's going to be it's going to select them wrong. So you see I clicked on that joint and it's saying planar. Planar is as if I have my mouse rolling across the table. Or it's stuck on the table. I want this to be translational. Translational is when we have something sliding through a groove or a slot in something else. And I'm going to go through and I'm going to change each of these to translational. And then I'm going to come to here, and this is going to be my hinge joint. And this one here is going to be a hinge joint as well. And now everything should be locked together. Now, just for fun, because I'm interested if it'll work, I'm going to define these. So that's planar. This will be planar. Oops. This will be planar. This will be planar. This one and this one. So why I'm saying it's interesting is I'm curious to see what happens. This can either potentially be run through joints to guarantee that contact between there, or if it doesn't work, we're going to have to go and define contacts. But let's see what happens. Okay, so now we're good to go there. So just for fun, let's come here and we'll analyze the motion. Actually, let me stop that because I also want to make sure at 1.5 seconds, that's fine. So let me run that. And I always, every once in a while, I'll just pop in a quick run motion just to make sure I've got things going the way I want. So now let's analyze it. Okay, so nothing's doing anything. That's good news because it means that everything is joined together properly. So now what I want to do is I'm going to come here and I want to drive this little wheel here. So I'm going to come and I'm going to hide that bottom base there. And the reason I want to do that is because the way I'm going to create the motor. I'm going to come here, I'm going to grab the motor, and I'm going to tell it, you notice how it snaps to the center. Well, it recognizes that that's the center of that cylinder, and by doing that, it attaches the motor to the cylinder, but at the center. If I had left the base there, I possibly could have attached the motor to the base, and that would have been bad because it wouldn't, the base is grounded so it can't move. I'm going to change this to angle, and let's rotate it 180 degrees. Turn my base back on. Oops, there we go. And let's come back to my motor just to check it here. So it's a step. Its duration is 0.5 seconds. I'm running this for 1.5 seconds, so we'll make it run the full duration. And now let me analyze it. And unsurprisingly, it's rotating, but it's not doing anything to my gear here. And the reason it's not doing anything to my gear is because I haven't defined contacts. So we're getting closer. So now I'm going to come to my contact. I'm going to pick my gear for part 1. My second gear for part 2, click Create Contacts. A little trick here, I'm going to come back to my animate and I'm going to change, or to run, I'm going to change this to when finished. It tends to run a little bit faster if you're not constantly animating while you're running. So now I'm going to run it. This will take just a little bit of extra time. I've got a whole bunch of joints, but more importantly, I have that contact. Contacts are what really bog down the analysis, but this should probably only take about 30-45 seconds to run. We can, I don't know what the definition on this, but we can hopefully see that little circle beginning to rotate there, or to spin around. As soon as that gets to the end, we get that little blue check mark. And now if I come here and I animate it, look at that. Okay, so that was what I was afraid of. Not surprisingly, but just wanted to check it. So those joints aren't working. It actually has to be a contact. So let me just come here to the joints here, and we're just going to go to free. I'm just going to turn off these joints here, these planar joints. Actually, I probably don't even need to do that. So I'm going to come to my contact. So now I have to come through and I have to define a contact. So a contact between here and that part right there, create it. And now come to my contacts. Oops. Stop it. Why does it keep having those selected? Okay, that's great, but I don't want that contact. Oh, because that contact selected. There we go. So I just clicked off to deselect the contact. Okay, grab this right here, select this, create the contact, click off here so it deselects the contact. Click this one, part 2, create, part 1, part 2, create, and now finally part 1 and part 2, create. So now I have contacts going all the way around. We'll get out of this. We'll run this again. Let me let's go down to 30 hertz. The less points I take, the quicker it'll run. Obviously, if I were doing this for real, I could deal with an extra couple of seconds or couple of minutes of run time to get a finer resolution. But just to make sure that we're going here, looks like I've got enough time on my laptop, and so far the Wi-Fi is holding out in my dark room here. But I want to make sure we get through this before I potentially lose power. I can see people scampering out of the dark building. So in the couple of seconds that we have, any questions arise? I know this is the drama of watching paint dry. So if I had animate while solving, we'd actually be seeing it move, but it would take, I won't say substantially longer, but it does increase the time, because then not only is it going through and calculating the actual behavior of it, then it's also having to calculate the animation at the same time, and it just unnecessarily bogs down the processor here. So just I can wait to see the end. So can you repost the link to the day 2 material? Absolutely, I can. Give me just a second here to come here and recopy it, copy to clipboard, and come back to my chat window, and let's paste it right in there and send, and there you go. That process should have taken a little bit longer than. So my concern now is with as long as it's hanging here, I may have something hanging up. So I'm going to stop this and let's run it. Okay. So you see my problem, and that's why I'm glad I stopped it. So I noticed that I don't know whether the resolution allows you to see that circle spinning around, but it hung at the same place for quite some time. And when it does that, that usually means that something's going wrong. And can you see what's going wrong here? Bam, I'm hitting right there. I have not completed my full 180 degrees, but these, as a result of the contact, have now smashed into the end here because this pulley isn't really, I mean, it can go out, but I was really hoping it would go in. So it was hanging there because it couldn't figure out what to do. That angle, it couldn't reach an angle. And that's why I was saying it's going to hit that, whatever you set, unless it physically can't. And this is a case when it physically can't. So it's going to sit there for a little bit, try to figure out, okay, what can I do to figure this out? And when it finally says, not going to happen, it probably would have errored out. So simple solution, right click to get out of here, double click on my motor. Now watch closely, let me zoom in a little bit here. Watch that arrow, I'm gonna click plus minus and bam, motor's going in the other way. Now let me run it. See now, that would have been a case for animate while solving would have helped me because I would have immediately seen that there was a problem going. So there is an advantage to animate while solving, especially when you're in kind of that initial debugging time state. Now look how quickly this thing's whipping around here. So it's useful in that initial debugging, but once you have all the bugs worked out and you just keep running run after run after run, go ahead and turn that animate while solving off. It's going to make your runs go faster. And now let me come here and animate that, and sure enough, there we go. Now if I wanted to make this even cooler, I could come here to my motor. And we're seeing, and now I'm seeing the torque required to do that, so I can get information. So this is now going to help me determine the size of the motor that I would need to run this system. This motion stuff is awesome. There is so much you can do with it, and so much information you can get out of it. And you see this right here. How long did it take me to do this? And I was talking through the whole thing. It took me, what, 5-7 minutes to set this whole thing up? That's the beauty of this Inspire Motion stuff. Where else are you going to be able to get the exact torque requirement for a motor to drive this system in 5 to 7 minutes? Okay, enough jabbering on about that. Let me come back here to the motor. Oh, darn it, I keep forgetting to, let me get out of the motion. And there we go. Come here to the motor. We'll make it step, dwell, step. So it's going to start at 0. It's going to step 5 seconds. We're going to dwell for just 1/10 of a second, and then 5 seconds to come back. And we'll run it. And now we can see this thing kind of go out and back in. So right now it's just converting. Before it starts running, while that thing's spinning, it's converting all the information necessary to send it to motion solve. Now it's actually running the solution, and then we should be back with this in about five seconds. And now I animate it, and now we can see it run in reverse. Okay, I'm going to sound totally geeky here, but how cool is that? I mean, that's why I love this motion stuff, because this is high-end stuff. To be able to do this in a motion process, even in our motion processor, it's going to take me days to teach you the software, and then you got to figure all this stuff out. Do it Inspire. This is so wickedly fast and really cool. And okay, I'm done geeking out here. I went through this a little bit faster than I normally would have, but again, I just wanted to make sure that I get all the information out there in case the catastrophic failure that we're having here in the building gets worse and I lose my connection. But essentially now that leaves me at a point where I have shown you everything that I wanted to show you. Uh, the class, you've got the class material. You got my contact information if you want to talk to me about it or arrange a sponsorship or a visit out to your team or whatever. Um, I'll open the floor to any questions that you have about the motion stuff. Get this, get a sponsorship. This stuff is awesome. You know, and that I see a question pop up. Just give me a second here. If you're on a competitive team, I've helped Baja teams come up with incredible suspensions and lightweight their vehicles. We've helped Formula teams. I've even helped clean snowmobile teams. Robotics teams use this to simulate, you know, these robotics teams are having to come up with things, whether you're talking FIRST or the student design competition through the ASME. They're having to design very kinematic robotic systems. You can simulate it all in here, determine the motors that you're going to need, all that sort of stuff. I'm sorry, but if you covered Force Explorer. Yeah, so the Force Explorer here, come on. All what the Force Explorer is going to do is it's going to show me my contact forces. It's going to give me these arrows indicating what forces I'm seeing in my contacts. I could actually see the same thing if I come here. So I've got this contact was the one I created first. If I click this, it should pop up a graph here. So this graph is my contact force between this gear and this gear, and that is a graphical representation of these arrows that I'm seeing here. So forces, text, show text, always on top. Implicit joints, I'm not sure. Honestly, I'm not sure what that's going to be showing. Hide motor forces. What's this? Show joint forces, so I can show the joint forces in there as well. So you see as this is moving, I'm getting some moments, I'm getting some normal forces. So it's a way of determining what the actual forces are and just visualizing those. The nice thing is I can pause this. I now have everything right here. Let me turn this off. I could snap a screenshot of this and show people what's happening graphically at all my forces at any point in time. And you include the landing gear with right. Oh yeah, yeah. Yes. That's a big file, but let me see what the file size is. So give me just a second here. Power motion demo, which is landing gear. Where sort by landing gear. Oh, that's not that bad. Yeah. Okay. Yeah. Let me Let's WinZip it. Add a zip file. Okay. Actually, you know what? So I'm going to zip this up, but before I send it out, I probably should make sure that this is a file that is not just a demonstration file, that it's one we can distribute. But let me do this. So I'm going to see who else is here. And let me just grab a screenshot of this. Got it. And picture and done. Okay. So I will. I have all your email addresses in the registration thing. I'll send this out. I don't want to distribute something that I'm not supposed to distribute. So let me get the okay to distribute that first, and then I'll send out a link to you. It'll be the same type of link that you got, and then you can play around with that too. Motion simulation and individual fire. Visualization. Yeah. Oh, sure. Yeah. No problem. great question. So somebody's asking if I can show the optimization. Actually, one of the demo files I have here, and if I can distribute these, I'll include this one as well. Um, Desktop demo, and it was a rotary engine, radial engine. Okay, so again, this isn't something that I'm going to show actually running because it would take quite a bit of time to actually run the optimization. So what we'll do is just show the what we do to set this guy up here. Okay, so I've got this simulation here. Darn it, let me load that up again. So this is a rotary engine. So like a piston-driven engine on a propeller aircraft, for instance. So we got a rotary engine. No, the motion's just not there. It's actually kind of an interesting design here because of the way that they're simulating this. I like this model because sometimes you have to kind of think outside the box. So imagine what this engine is going to be doing. We know that in a combustion engine, we get an explosion here. It forces the piston down. It causes that to turn, and then this one, and this one, and this one, and we're going to go all the way around, and we're going to get that. But obviously, we can't have an explosion. We can't have the explosion driving it. So what somebody did is they put a motor on here. If we come down here, because their goal is to optimize this little rod right here. So they put a motor on here to cause it to spin. But what happens when we're spinning it? So we're kind of taking a look at in reverse. To spin it, remember that with a combustion engine, the piston does two jobs. The first thing it's doing is it's compressing the gases in there, and then when they explode, then it goes in the other direction. But I'm not getting that behavior of that gas compression. So what they did, and this is what I really like because it's really kind of ingenious, they hid them so they're not distracting from they put a bunch of coil springs on there. Some pretty stiff coil springs, 1,000 newtons per millimeter, and that's going to represent the behavior of that compression. So let me run the analysis here, or run the motion. Just a second. So there you go. So you see it's spinning it and it's going around and compressing that. So we're actually getting forces and stresses inside these little rods here. So it's actually representing what this engine's going to do. Cool. So now we can animate that. So you see there's the behavior of that going all the way around. So that we're talking the main driving rod here. We also want to optimize that. So let me get out of the motion. So what they did now, and I'm going to click on this rod, and I'm going to click I for isolate. So we're going to isolate this rod here. And look what we've got. We have a design space. And then if we come up here, not those. Which one is shown? Go there, it's Conrad. And now let me turn these on right here. I have my little non-design spaces. So if you were with us with Inspire analysis and optimization, or if you're just familiar with Inspire, we know that to do an optimization, we need a design space, what can be carved away, and we need non-design spaces to make sure that this can connect properly or contact things properly, and that's what we've got here. So this is no different than a normal Inspire optimization, except for the fact that as opposed to putting any forces on here, and in fact, you'll even notice I have symmetry planes on here. I've got two symmetry planes to guarantee it's symmetrical left and right and top to bottom. And they've done and gone and put a split draw manufacturing constraint on there. So this is no different. I could take this, I could constrain it at the center here, or put a torque at the center here, constrain it there, or put a force there, whatever, and I could run an optimization. But as opposed to doing that, and that's where the beauty of this is, it's going to get all of its forces from the motion. So now when I come to optimize the part, it sees, okay, that's the one design space I have in here. And I'm going to click use all 31 time samples. So it's going to use all of those different forces, because the force is going to change as it goes around. The angle of this is going to change. So I've got essentially 31 different load cases that I'm going to optimize against. How cool is that? And what I get is that with whatever print, they did 2 optimizations. So their ball joints or pin joints, max stiffness, and ball joints. Oh, okay. So what the joint was. So this is, they put a ball joint between there, and this one, it was a pin joint as opposed to a rotating ball. And then they got those 2 shapes there. So that's how we can drive an optimization using the motion. It's no different than running an optimization normally in Spire, except for the fact that we, as opposed to putting forces in, we put the motion values in there, and it will calculate the forces for you. This would be, imagine how crazy insane it would be to come up with accurate forces for this rod through the entire motion of this rotary engine. That would be absolutely crazy, but yet the simplicity of this is I could have set this up. Now this is a little bit more complex, probably take me a good half an hour, 40 minutes to get this set up properly, but not that overly complex. And just like that, I'm running an optimization on there, and I have no clue what the forces are. I could get them off of here, but I don't have to know. And that's that. So hopefully that answered your question. I know it was a bit of a long answer, but I think we kind of covered it fully. So any other questions before we wrap things up? Still saying I got 35 minutes on my laptop, so things are looking good. My biggest concern now is just whatever backup system they've got our Wi-Fi routers on, or batteries that they have in those. I know they got them spaced around the office here, so hopefully those will hold out. But again, even if I were to lose power right now, I got you all the information that I really wanted to get you. If you're on a team, let us help you. If you're, I don't want to say just a student. If you're a student not affiliated with the team, get your hands on the student version. Take a look at altairhyperworks.com. That's what I was going to do. I forgot about that. See, I promise things and then I forget about them. Altairhyperworks.com. We still got the internet. If you come here to support and training and come to course schedule, and then view all regions, come to online and view schedule. Here's a listing of all of our online courses that we offer. And you see there's a full Inspire Motion in November. Yeah, that's the next one. We're still trying to, this is a relatively new class, so we're still trying to suss out what the best timing on that class is. What do we got here? What kind of help do you offer? Design feedback or troubleshooting? What help do you? Troubleshooting. So if you are a sponsor, so if you're a student and not affiliated with the team, you have the student version. What you can do is get on. So if I come here to altairuniversity.com, we have this support forum. So this is where students can get assistance in anything. So you'd come to multi-body simulation, so Altair Inspire Motion. You see 1,336 people have asked questions. So, take a look in here. All sorts of topics. I've never actually done this, so I don't know where the actual questions are. Here we are. So, you can come in here. Other students, other faculty, other people in education will answer it. Or, Raul, for instance, he's one of our administrators. He's an Altair employee. If things aren't getting answered, he'll hop in there. Chris Coker's another one of our masters of multi-biodynamics. Sometimes they'll get in there and answer it. But if you're a sponsored team, then I'll work with you. We can do webinars. We can do live visits to do support and training. You run into a problem with it. You do so with the teams. Support a sponsored team. We will get the name of one or two. I can't remember whether it's one or two people who can contact our main support directly, and then also I can work with you on consulting as well. For sponsored student teams, yes. Yeah, so for sponsored student teams, if you're sponsored, we should have already gotten the name from you that can contact support. Otherwise, I can work with you. We can do webinars, or if in my travels I can get out to there directly. We can see about setting up trainings and. So we're not going to design the parts for you. Obviously, if you wanted that, you wouldn't be involved in the competitive teams to begin with. But all the time I have people bounce questions off. Now, just looking here, so you're okay. So you're in Alberta, Canada. So you would be handled through our Canadian office. They will provide support to teams. I know that the country manager in Canada is very, very supportive of education, so they're going to help you out as well. If you get in touch with us, we can put you in touch with the appropriate person. So if you go through that sponsorship, that's for the U.S., but they will pass the admin who gets that information will pass that information off to our Canadian office, and they'll pick you up from there, and they'll offer you the same level of support that we're going to offer here. I do strictly U.S. teams. And sometimes outside of the U.S. if we don't have an office in that, but we have a very large Canadian office that can help you out. So. But yeah, design feedback, troubleshooting, yeah, we're there to help you. Okay, so that's pretty much it. I hope you got something out of it. I had a lot of fun with this one. I love Inspire Motion, in case you couldn't figure that out by my overall geekiness about it. But I love working with it, love showing it off, love helping people. You'd be amazed at what you can pull off with Inspire Motion. It's an impressive software. So get involved with it. Let us help you out. Other than that, thanks a lot for your attendance. Keep your eyes out for the rest of the webinar series. So you're very welcome. We've got many more weeks of the webinar series coming up. Some really good experts who are going to help you out there. If you haven't signed up for them, sign up for them. I think the next one's OptiStruct, but excellent. Thanks for stopping by. Thanks for your time. I know 2 hours of time is quite a bit to ask of you, so thanks for your time. Thanks for sticking with me. And then ultimately look for an email indicating how you can view the recordings of this as well. So thanks a lot. Take care of yourselves and have a good, well, not quite the weekend, but have a good weekend.